In section 2.1, we look at our second definition of the 6 trigonometric functions. And this definition is called right triangle trigonometry. Let's first review our right triangle here. So when you have a right triangle, what that means is that we have a 90-degree angle as one of the angles. And that's indicated by this little square here. If we call our triangle ABC, out of convention, we always label C as the right angle. A and B are the acute angles of the triangle. And let's remember that when you have a triangle, we know that the sum of the angles of that triangle is always equal to 180 degrees. And because angle C is 90 degrees, that means that angle A and B have to add up to be the other 90 degrees. So anytime you have a right triangle, the two acute angles of the right triangle are always complementary. In other words, they add up to 90 degrees. For the purposes of defining our 6 trigonometric functions in a right triangle, we are going to focus on one of the acute angles. And the acute angle that we focus on here is angle A. And I want you to notice that with respect to angle A, side A is opposite angle A because it is across from angle A. Side B is next to angle A because it is touching angle A. And so when that happens, we call it the adjacent side. And side C is what we always refer to as the hypotenuse. So now let's talk about the 6 trigonometric ratios. For angle A, we define the sine of angle A to be the side that is opposite angle A divided by the hypotenuse. So again, in this picture here, here's angle A. The side opposite angle A is side A, and the hypotenuse is side C. And so the sine of angle A is A divided by C in this picture. The cosine of angle A is defined to be the side adjacent to A divided by the hypotenuse. And again, the side adjacent to angle A is side B. And so this is B divided by C. And the tangent of angle A is defined to be the side opposite angle A divided by the side adjacent to angle A. And in this picture, that is A divided by B. Now, the other 3 trig functions can be found by simply taking reciprocals. So remember that tangent and cotangent are reciprocals. And so if tangent is A divided by B, then cotangent is B divided by A. Likewise, cosine and secant are reciprocals. And you'll notice that cosine of angle A is B divided by C, and secant of angle A is C divided by B. And finally, sine and cosecant are reciprocals. And so the sine of angle A is A divided by C, and the cosecant of angle A is C divided by A. Next, what I want to do is show you a way to remember these relationships a little bit more easily. So if you notice that the sine function is defined to be the opposite over the hypotenuse, the key letters to focus on is that sine begins with the letter S, opposite begins with the letter O, and hypotenuse begins with the letter H. So you can think of that as SOH, which means sine is the opposite side divided by the hypotenuse. And we think of that as so. That's the way we pronounce it. So that's the SOH here. In a similar way, if you look at cosine, you'll notice that cosine is adjacent over hypotenuse. And so we can think of that as CAH. Cosine is adjacent over hypotenuse. And we pronounce that ca. And finally, for tangent, which is opposite over adjacent, we can summarize that by the letters TOA, which is pronounced TOA. And so altogether what we have is so, ka, TOA. And this is a nice way to remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now what I want to show you next is that this second definition is actually equivalent to the first definition that you were given in Chapter 1. So in Chapter 1, we defined an angle theta to be in standard position, and if we assume that that angle is in the first quadrant, this is what the picture would look like when you pick a point x, y on the terminal side of theta. And from here, we know that sine of this angle, theta, which I'll think of as the angle A, is y divided by r. Cosine is x divided by r. And tangent is y divided by x. Now, if you just take this idea and superimpose a right triangle ABC on top of this triangle here, then y is the same as side A, x is the same as side B, and r is the same as side C. And we know that sine is opposite over hypotenuse, so that's A divided by C, etc. Well, notice that A divided by C is the same as y divided by r, right? Because we're just taking this side and dividing it by this side, and over here we're just taking this side and dividing it by this side. So the key point to make here is that the definitions are the same, but the second definition is a more convenient definition when we are working inside of a right triangle. Because in that case, we don't have to put the angle in standard position. We can just look at the acute angle in the triangle. Now let's take a look at an example. In our first example, it says, find the 6 trigonometric ratios of angle A if side A is 4 and side C is 5 in right triangle ABC. So now the first thing I want to do here is draw a triangle that represents triangle ABC. And we know it's a right triangle, so we're going to draw it so that it has a right angle. And we know that the right angle has to be angle C out of the convention that we mentioned earlier. Now I can put angle A or angle B in either of these slots, but I'm going to put angle A here and angle B here. Now in terms of the sides, we know that side C is 5, side C is opposite angle C, and we know that side A is 4, and side A is opposite angle A. And so that means that this missing side right here is side B. So the first thing we need to do, if we're going to find the 6 trigonometric ratios, is we need to find side B. And we could do this using the Pythagorean theorem. So we know b squared plus 4 squared is equal to 5 squared. That's the same as b squared plus 16 equals 25. Subtracting 16 from both sides, we get b squared is equal to 9. And when you take the square root of both sides, we end up getting b equals plus or minus 3. But again, since b represents the length of a side of a triangle, b must be 3. So let me go ahead and label that in our picture here. B is 3. And now we have all the sides of the triangle, so we should be able to find the 6 trigonometric ratios of angle A. So let's go ahead and compute these. Now remember, we are focusing on angle A, which is right here. And so when we go to find the sine of angle A, we need to remember that sine of A is the opposite side, which is 4, divided by the hypotenuse, which is 5. So the sine of angle A is 4 divided by 5. The cosine of angle A is the adjacent side, which is 3, divided by the hypotenuse, which is 5. So the cosine of angle A is 3/5. And finally, the tangent is defined to be the opposite side divided by the adjacent side. And so for this triangle, that's going to be 4/3. Now to find cosecant, secant, and cotangent of angle A, all we need to do is take the reciprocal of the correct trig function. So cosecant is the reciprocal of sine, so that means it's 5 divided by 4. Secant is the reciprocal of cosine, which will be 5/3. And cotangent is the reciprocal of tangent, which means it will be 3/4. One final note about this triangle is that this is a very special and a very common triangle that we'll be seeing all throughout the semester. And this is what we like to call the 3-4-5 triangle. The 3-4-5 triangle is always a right triangle, and it means that the legs of that right triangle are always going to be 3 and 4, and the hypotenuse is always 5. So anytime you know two sides of a 3-4-5 triangle, you can always find the third side by simply memorizing the fact that we have a 3-4-5 right triangle. Now, one key thing to remember here is that 5 has to be the hypotenuse in this case. All right, let's take a look at another example. So in our next example, we want to find the sine of A, cosine of A, and tangent of A, and the sine of B, cosine of B, and tangent of B for each of these two triangles. So we'll take them one at a time. Now again, to find the 6 trigonometric ratios, or in this case, the 3 trigonometric ratios, first we need to know all sides of the triangle. So in the first triangle, this side over here is side C. And we know from the Pythagorean theorem that 1 squared plus 2 squared must be equal to c squared. That means 1 plus 4 must be c squared, or 5 must be c squared. And if we take the square root of both sides, we get c is equal to plus or minus the square root of 5. But again, c is the length of a side of a triangle, and so it has to be positive. So c is radical 5. Now I'll go ahead and fill that in here. So now let's find what they're asking for. To find the sine of A, again, I need to locate angle A, which is right here. And sine is defined to be the side opposite angle A, which is 2, divided by the hypotenuse. Now the hypotenuse is down here in this case. So sine of angle A is 2 divided by radical 5. And again, you can leave your answer like this, or you can rationalize the denominator and get 2 radical 5 over 5. Cosine of angle A is the adjacent side divided by the hypotenuse. Now, the adjacent side is the side that is next to angle A, but the side that is not the hypotenuse. And that means it's this side right here. So the cosine of angle A is 1 over radical 5. And again, if you rationalize the denominator here, you will get radical 5 over 5. And finally, the tangent of angle A is the opposite side, which is 2, divided by the adjacent side, which is 1. And so it is 2 divided by 1, which is 2. Now, when we take a look at angle B, what we have to do is change our perspective. So to find the sine of angle B, again, it's defined to be the opposite side divided by the hypotenuse. But for angle B, 1 is the opposite side, and the hypotenuse is still radical 5. And so this is 1 over radical 5, which is equal to radical 5 over 5. The cosine of angle B, we have to take the adjacent side. The adjacent side to angle B is 2, and divide that by the hypotenuse, which is radical 5. And again, you can rationalize the denominator. And finally, the tangent of angle B is the opposite side, which is 1, divided by the adjacent side, which is 2. So the tangent of angle B is 1/2. Now you might notice that the cosine of A and the sine of A and the cosine of B are the same. And you might also notice that the cosine of A and the sine of B are the same. And that is not a coincidence, and we'll talk about that in just a minute. Let's go ahead and take a look at the next example. So again, we have a right triangle, and we want to find sine, cosine, and tangent of each of the acute angles. Notice that in this triangle, we do not know what side A is. And again, this is side A because it is opposite angle A, right? So let's go ahead and solve for side A. We know that a squared plus x squared is equal to the quantity 2x squared. This is a squared plus x squared is equal to 4x squared. Subtracting x squared from both sides gives us a squared is equal to 3x squared. And finally, taking the square root of both sides gives us a is equal to plus or minus the square root of 3 times the square root of x squared, which is plus or minus the square root of 3 times x. And we can rewrite this as plus or minus x radical 3. Now, once again, let's remember that A is the side of a triangle, and the side of a triangle cannot be negative. So A is x radical 3. Now, let's go ahead and label that in our picture and find the trig ratios. Now, I'll go through this just a little bit faster, and also I'm not going to rationalize any denominators this time. Angle A is here. Sine of angle A is the opposite side divided by the hypotenuse. And so that is x radical 3 divided by 2x. And the x cancels out, giving us the square root of 3 divided by 2. The cosine of angle A is the adjacent side divided by the hypotenuse, which in this case is x divided by 2x. And when you cancel the x's here, you get 1/2. Remember, there is an invisible 1 up here. Tangent of angle A is the opposite side divided by the adjacent side, and so that is x radical 3 divided by x. Again, we can cancel out the x, and we get radical 3. Now let's focus on angle B. Angle B is up here. Sine of angle B is the opposite side, which is x, divided by the hypotenuse, which is 2x. And again, canceling the x, you get 1/2. Cosine of B is the adjacent side divided by the hypotenuse, which is x square root of 3 divided by 2x. Cancel the x to get radical 3 divided by 2. And finally, tangent of angle B is opposite over adjacent, which is x divided by x radical 3. And in this case, this is 1 over radical 3. So again, to find the 6 trigonometric ratios in a right triangle, you have to know all 3 sides. And if you have a variable as a part of one or more of the sides, you'll likely have a variable in the missing side as well. But notice that in the end, that variable doesn't really matter because it cancels out. So now I'm going to talk about something that we call cofunctions. Sine and cosine are cofunctions. tangent and cotangent are cofunctions. Secant and cosecant are cofunctions. So they have the same root word, but the other one has a C-O, in front of it. Now, we already saw that the sine of angle B is B divided by C in a right triangle. And that's the same as the cosine of A. So if you just take a look at a right triangle, ABC, here's side A, here's side B, here's side C. Again, remember that the way you label it is the letter of the side has to match the letter of the angle that is opposite it, right? So side B is opposite angle B, etc. So again, sine of B is the opposite side divided by the hypotenuse, and cosine of A is the adjacent side divided by the hypotenuse. So you can verify that sine of B and cosine of A are equal. And we can actually do this for all of the co-functions. Tangent of B is the same as cotangent of A. Secant of B is the same as cosecant of A. And then we can switch the A and B around to get the other relationships. Now, what's so special about A and B? Well, in a right triangle, we know that A plus B is always 90 degrees. That means they're complementary. So that leads us to something that we call the cofunction theorem. The cofunction theorem simply says a trigonometric function of an angle is always equal to the cofunction of the complement of the angle. And let's remember that if you have an angle x degrees, the complement of that angle is 90 degrees minus x degrees, right? So the complement of x is 90 minus x. So the way we can say this cofunction theorem in a very efficient manner is that sine of x is the same as cosine of 90 minus x. Likewise, cosine of x is the same as sine of 90 minus x. And we can do the same thing for tangent and cotangent, and also for secant and cosecant. Now let's take a look at some examples. So in the first example, it says that tangent of 8 degrees is the same as cotangent of what? So what we need to do is simply find the complement of 8 degrees. Now the complement of 8 degrees is 90 degrees minus 8 degrees, which is 82 degrees. So tangent of 8 degrees is the same as cotangent of 82 degrees. And we could do the same thing for all of these. So secant of 73 degrees is the same as cosecant of 17 degrees. And that's because 73 degrees and 17 degrees add up to 90 degrees. Now the last one says sine of x is the same as cosine of what? Well, again, we need the complement of x, and we know that that is 90 minus x. Likewise, we can do it when we reverse the relationship here. So cotangent of 12 is the same as tangent of 78. Cosecant of 63 degrees is the same as secant of 27 degrees. And the sine of y is the same as cosine of 90 minus y. Now the last thing we want to do in this section is focus on our special triangles. We have one special triangle, which is the 30, 60, 90 right triangle, and the other one is the 45, 45, 90 right triangle. And what I've done here is I've labeled the sides of that triangle. In the 30, 60, 90 triangle, I'm labeling the short leg as t. We already know the longer leg is t times radical 3, and we know the hypotenuse is twice the short leg, which is 2t. Likewise, in a 45, 45, 90 triangle, both of the legs are the same, So we'll call those t, and the hypotenuse is the leg t multiplied by radical 2. Now, what I want to do is focus on the trig functions of 30 degrees, 45 degrees, and 60 degrees by looking at these triangles. And I won't go through all the relationships, but let's talk about a few. Let's focus on the 60-degree angle. We know that sine of an angle is the opposite side divided by the hypotenuse. So the sine of 60 degrees is the opposite side, which is t radical 3, divided by the hypotenuse. Yes, by the way, the hypotenuse is not this side. It is 2t. And when you cancel the t, you get radical 3 over 2. And you can see that here in the table. The sine of 60 degrees is radical 3 over 2. We could do the same thing for any one of these other angles and any one of these other functions. So I'll do a couple more just to show you. What if we were looking at the 30-degree angle? And let's say we wanted the tangent of 30 degrees. Well, the definition of tangent is opposite over adjacent. So in this case, that would be t divided by t radical 3. And when you cancel the t, you get 1 over radical 3. And 1 over radical 3 is the same as radical 3 over 3 if you rationalize the denominator. And then I'll just point out to you that in the table here, here's 30 degrees and here's tangent. So the tangent of 30 degrees is radical 3 over 3. And we can do the same thing for the 45-degree angle as well. And if you do that, you get this table here. So we have all those values summarized in the table right here. And then for 0 degrees, we can use our old definition, right? So if I want the sine of 0 degrees, I can't use the new definition for that because there is no such thing as a 0-degree angle in a right triangle. So for 0 degrees, we have to draw an angle in standard position, 0 degrees. We have to pick a point on the terminal side of that angle. My favorite point to pick on the angle 0 degrees is the point 1, 0. And if I want the sine of 0 degrees, we have to remember that that is y divided by r. So we have to take the y value, which is 0, and divide it by the r value. Now the r value is this distance right here, and that distance is 1. And 0 divided by 1 is 0. Okay, so that's how we know the sine of 0 is 0. You could do the same thing for cosine of 0 and for tangent of 0. And then for 90 degrees, you would also do the same thing, except that you would draw an angle in standard position that represents 90 degrees, which would be this angle here. Pick a point on the terminal side of 90 degrees, like the point 0, 1. Again, for that one, r is equal to 1. And from there, I can find the sine or cosine or tangent of any of those angles. So as an example, tangent of 90 degrees, tangent is y divided by x. And for 90 degrees, y is 1 and x is 0. And so that's 1 divided by 0, and 1 divided by 0 is undefined. So this table gives you a nice summary of sine, cosine, and tangent of all of the important angles between 0 and 90 degrees. So what you'll want to do eventually is you'll want to memorize these values. And I know that might seem like a lot at this point, but we use these values so often that, believe it or not, sooner or later, you will memorize these values. Now, just a few final examples. Suppose I asked you to evaluate the following mathematical expressions. So in the first expression, we have 2 times the cosine of 30 degrees quantity to the second power. So to do this, the first thing we need to do is we need to ask ourselves, what is the cosine of 30 degrees? Well, we can get that value from the table on the previous page. And here is that table for convenience. So if you look at 30 degrees, the cosine of 30 degrees is radical 3 divided by 2. So to evaluate this expression, it's going to be 2 times the cosine of 30, which is square root of 3 over 2, quantity squared. Now I just need to simplify that expression. I can cancel the 2 here, and we get radical 3 to the second power. And that, of course, is just 3, because the square and the square root cancel each other out. Now I could do the same thing for the next example. Here we have the sine of 60 degrees. Sine of 60 is radical 3 over 2, plus the cosine of 60 degrees. Cosine of 60 is 1/2. Quantity to the second power. These already have a common denominator, so we can add them together. Square root of 3 plus 1 over 2, quantity to the second power. And that means we're going to square the top, and we're going to square the bottom. Now, squaring the top means multiplying this expression by itself. So next we need to multiply this out. And if we do that, we get radical 3 times radical 3, which is 3. Radical 3 times 1 is radical 3. 1 times radical 3 is radical 3. And 1 times 1 is 1. Divided by 2 squared is 4. And if we combine like terms, 3 plus 1, that's equal to 4. And radical 3 plus radical 3 is 2 radical 3 divided by 4. And then one final thing that we can do is we can cancel a factor of 2 in each one of these numbers. So if we do that, 4 divided by 2 is 2, 2 divided by 2 is 1, and 4 divided by 2 is 2. So as a simplified answer, this is 2 plus radical 3 divided by 2. And we'll leave our answer like that. And no, you cannot cancel the 2's here, right? Because those are terms on top, so we cannot cancel these. All right. The final example here, we have a variable expression, 2 cosine of the quantity 3x minus 45 degrees, and then they tell us that x is 30 degrees. So to evaluate this expression, we'll just plug in 30 degrees for x. So we'll plug that in here. That gives us 3 times 30 degrees minus 45 degrees. Now let's do the math here. 3 times 30 degrees is 90 degrees minus 45 degrees. 90 minus 45 is 45. And the cosine of 45 degrees, it's up in the table there, is radical 2 over 2. And then now the 2's simply cancel out, and we end up getting radical 2.